Hi, I'm Devendra Kapadia. I'm manager of calculus and algebra at Wolfram. And at 10:30 a.m. this morning, I speak with Adam Strzebonski, a senior developer, on what's new in calculus and algebra. It should be very exciting. Do come there. Thank you.
So this is talk, what's new in calculus and algebra. I'm Adam Strzebonski. It's joint talk with Devendra Kapadia. He will finish the talk. So let me start with what's new in algebra first. So the root objects. We have changed the display format of root objects. So if you evaluate a root object now, you will get something like this short form that just shows the approximate value. It's still an exact number, and there is nothing has changed in the underlying expression. It's just a display form that's shorter and more readable. So, and another change related to root objects is that the new default setting for cubics and quartics option in solve is automatic, which means that if all the coefficients are numeric, so the roots are numbers, then they are returned as root objects rather than as radicals. So we'll not use Cardano formulas to solve third and fourth degree equation with numeric coefficients unless you ask for it. So that's what we get from solving a quartic right now. And to get the radicals that Mathematica used to produce, we have to set quartics explicitly to true, and we get the solution in radicals. So let me give you some motivation for the change. So my claim is that root object representation is much more useful for further computation. That's why we switched. So first, let's try the numeric approximation. The difference here will not be that large, but it's still slightly faster to compute with root objects. However, if we do some more complicated computation, like inverse a matrix with entries that are root objects or radicals, then with root objects it's half a second. With radicals, I will not evaluate it. It took 18 seconds. So the difference is quite large, and if we make the matrix larger, it will grow. So that's about root objects. Now another change. So in equation and inequality solvers, we can now do structure recognition. So that here are a few improvements in equation and inequality solvers. So structure recognition, vector and matrix inequalities, and Lazard projection, which I will shortly say what it is. So structure recognition. We can recognize triangular polynomial systems with finitely many solutions and do directly into solving for the solutions rather than try to compute, to prove algebraically that there are actually finitely many solutions. It may happen that if you have n equations with n variables, the number of solutions is still infinite, but it's a rare case, so it's more efficient to try to find the finite number of solutions and detect that it's not the case. We have infinitely many solutions rather than compute Grobner bases for everything. Then the Grobner base dominates the computation time. So here's a few examples. I will not evaluate them, just show them. So we have random polynomials of random homogeneous polynomials of degree 7, and we create a triangular system. So we have one polynomial, one variable, one polynomial, two variables, and so on. So here we go up to 5 variables, and we can get all the solutions, all the real solutions now in half a second. Took 289 seconds if we started with computing Grobner bases. And here's another example which we are looking for complex solutions. So here we find all the complex solutions satisfying the additional norm conditions. So we can have arbitrary triangular system and an arbitrary condition for basically we generate the solutions and check whether they satisfy the conditions. So it's an easy solving method, but here we can now find all the 1400 solutions in 5 seconds, and mathematical elementary didn't finish in 68 hours for this because of the Grobner-based computation. Block triangular system. So again, this is the case where the problem splits into a number of independent problems in disjoint subsets of variables. So again, here's an example with, so we take two n equations in two n variables, and basically there are just combination of pairs of equations in two variables. So if we take 10 equations with 10 variables, we can now get all the million solution in 40 seconds. Took 2,000 seconds in mathematical 11.3. And here is something. So if the number of solutions is too large, we can easily detect that we have a system with, like, here it's 2 to the nth solution. So if we make n equal 1,000, we will not be able to enumerate the solution. So in this case, instead of just hanging or running out of memory, we give a message and return one solution. So we can get one solution in 3 seconds, and this is the 2 to 1,000, I guess, the total number of solutions. So the next new things, vector and matrix inequalities. So this has been introduced mainly for numeric optimization, but it's also supported in symbolic solvers. So we can use vector inequalities and matrix inequalities. So this, for instance, says that the matrix is positive definite, and we get solutions. So here's something which contains a vector, component-wise vector inequality. We can solve it. We get the solution. Y is a vector, so that's why we get a pair here, right? And we solve for the general condition for positive definite matrices, and we get the result in terms of for symmetric matrices. Yeah, well, that's the part of the condition is that it's symmetric and positive definite. So that's encoded already in this symbol. Here we find a depth 3 array such that the first element of minus second element is positive definite, and it's an array of positive integers. Again, we have now this new domains where we can say positive integers, positive reals, positive rationals, and just for convenience. And we can also optimize with such conditions. So we minimize a Frobenius norm of a matrix with determinant 1, which is positive definite and has real entries. And we get the minimum is square root of 2. And here's the matrix. It's identity matrix for which the minimum is satisfied. And Lazard projection, it's slightly technical. So basically, it's an improvement in cylindrical algebraic decomposition algorithm, which makes it much faster for certain inputs. It has been long-standing conjecture that this projection is correct. It has been recently proven, and we have added it. And we can solve this problem in 14 seconds instead of 111. Okay, so the last topic is somewhere on the boundary between algebra and calculus. So asymptotic solve. So if we have a binary equation, then we can solve for one variable as a function of the other variable, right? So if we use solve, we get algebraic solutions that are global, but they are they don't really tell us how the solutions behave near any given point. So if we are interested how those solutions behave near 0, for instance, we can use series on one of those root objects, but unfortunately there is no one-to-one correspondence between root objects or root functions and series. So those functions have unknown branch cut structure pretty much. So if we use asymptotic solve, we can now get series solutions around the point x equals 0. Here we go. We got one power series for Puiseux series. And the advantage of asymptotic solving is that we can handle much wider collection of inputs. For instance, here we can start with something which is pretty much arbitrary analytic function, and we get a series solution near 0. And we can plot the result. See, we used the solution as a starting point for find root, so we can get the sort of exact solution of the equation, and we can see that the asymptotic solution to the exact solutions are pretty close near 0. They start off diverging farther away, but that's those. And there will be more about asymptotic solve in the next talk, and now I'm going to give floor to Devendra. Thank you.
Thank you, Adam. I'm going to talk about calculus, and I'm going to begin with pretty high-level stuff, asymptotics and special functions, and then move down a little bit to what our average user, college user would use, integral differential equations, and then finally talk about people who don't even use Mathematica yet, high schoolers, and people who want to learn calculus. So we'll start out high and then descend, but my main point is that a lot of this work is joint work with the team. Most of it is not mine, and I'll try and give credit, but really it's a team effort well beyond our own team, stretching to the training team. So let me begin with asymptotic calculus. So in version 11.3, we introduced asymptotic desolve value and asymptotic integrate for finding approximations to differential equations and integrals. And in version 12, we are now going to the discrete world of sequences, and we have two new functions, asymptotic R-solve value for difference equations and asymptotic sum for indefinite sum. So given a sum or a difference equation, we now try and get you an asymptotic, a simple formula that encodes everything you might want to know about the sequence. So as an example of this, here's a case where I've given a sequence. That's a sequence over here. It's some God-given sequence for now. Okay, and I say, someone says, find me an approximation for the 300th term of the sequence, right? So in version 7, Charles did a very nice job of putting up something called find sequence function, which will try and guess a formula. Well, in this case, what happens is find sequence function doesn't quite succeed. It gives back a difference root. So it gives back a difference equation. And of course, you can work with that. But now what we can do is we can take this thing over here and feed it to our new solver, which is asymptotic R-solve value. And I make sure to put a decimal point in one of the initial conditions. And then, lo and behold, it gives back an approximate formula. And that approximate formula is pretty good. But I said it's a God-given sequence. It's not quite that. I chose it very carefully, actually. So this sequence over there really is the sum of the squares of the factorials. So if you look at 42 and 618, then 42 plus 576 is 618, but then 576 is 24 square, and 24 is 4 factorial. So that's a very simple sequence, really. So I can also use a new function called asymptotic sum, which will do the same thing for you and give you back exactly the same approximate formula. Now, question is, all that's good, but how good is the approximation? Well, let's try it. So here's the 300 term with our approximation, that nice simple formula. And here's the exact result from sum itself. And you can see the approximation is pretty good given how little effort we took to obtain it. So that's the new theme. Given a sequence, find the 1000th term. We can do it for you now in a flash. Okay, so on to special functions. That's a heavy topic, but what happened is that we have documentation now which includes around 2000 scope examples for 100 functions in the system, and it's all borrowed from functions website, etc. And now what we do is we can find polar plots and all kinds of stuff on the pages which couldn't be seen early on. They look quite beautiful. We've done 100 of them, 150 to go. We'll finish soon, within a month or two. So when version 12 ships, we'll have 250 brand new pages for special functions. And let's say you want to learn about hypergeometric 2f1. That's an important special function. So now what I do is I go there, and let me enlarge a little bit so we can all see nicely. And now if I go down to the scope section, that's a mini functions website. It's got everything you want to know about special functions, in this case hypergeometric 2f1. So you might want to say, okay, what do the graphs look like? Well, we've got a nice set of graphs over here. And that happens for every single function in the system. That's really quite a big change. Okay, now hypergeometric is one level of special functions, but you need to go beyond that. So the new generation of special functions are what are called Hein functions. And these Hein functions, believe it or not, they are more general than hypergeometric. So hypergeometric functions are a very special case of Hein functions. And you see in the sentence over here, in one sentence I've blown away hypergeometric. I've said Hein G of something is hypergeometric 2f1. Hypergeometric is all absorbed into Hein. And why are they more general? Well, the hypergeometric differential equation has got 3 singular points, 0, 1, and infinity. And Hein has got 4 of them. There's one more over here. And that makes life quite difficult for everyone. Okay, so here's asymptotic desolved value telling you that you have one kind of regular solution at 0, and then one kind of singular solution. Now, if you've got 4 singularities, you can start merging them, being confluences. So there are 5 Hein functions, confluence ones, and then you've got 5 derivatives, so there are 10 new Hein functions. And you might wonder, why do you need them? I mean, why bother, kind of? But well, Tigran over here is a real expert on these Hein functions, and he's published, I think, 11 papers on this. One of them deals with 2-state quantum systems. So as we go forward in quantum computing, black hole theory, etc., we will need Hein functions, and they'll be there for you. This is the future for special functions. Hypergeometric is out, Hein is in. Okay, right. Okay, so let's go on a little lower now to differential equations. So over here we have desolve now gives back very nice constants, which eta did. And the nice thing is you can still plot them just like before. Nothing has changed, but you get nicely formatted subscript. That makes my own work very simple, because when I look at a solution, it looks nice now. The C1 and C2 look just right. Okay. The other thing is that on Stack Exchange there was a nice discussion about nonlinear ODEs, so I got inspired to solve a 20-year-old problem, namely how do you solve initial value problems for first-order nonlinear ODEs. Here's a hard example, and now it comes back in a flash with the correct solution. But then I asked reduce, how good is my solution? It said, oh, it only goes up to 1 over square root of 2. So I said, okay, let me take it over there. And now what I do is I give that old starting point as a new starting point, or the old finishing point, a new starting point over here, and I get back an equivalent solution. So you've got a nonlinear ODE, which has got 2 solutions, one which is kind of curved, one is flat, and together they make up the complete solution. So the solution which is equilibrium comes in from the left and just takes the old solution with it all the way up to infinity. That's pretty dramatic for me. I have not seen this before. And one last thing is that for a long time we have kind of had to cope with very hard integrals which desolve cannot do. So now we return inactive integrals. So over here you have a 4th order ODE I'm building up from the Bessel equation using differential operators. I get back the 4th order ODE. I solve it and desolve using factorization. It comes back in probably a couple of seconds with all the work done. There are integrals over there, but they're all inactive. And I can finally check the solution over here, and I get back a 0 almost immediately. There you go. Okay, so now the point is that this is a very important thing for us because there are some examples which would take 1 hour in 11.3, and now they finish up in 0.1 second. That's almost as good as the compiler next door. So I think we are really doing well over here. Okay, so on to symbolic integration. So we now can give constant integration. That's due to Michael Trott. He asked me to implement this. I did. So you get back constant integration, and you can do pretty difficult things. That's a, okay, thanks. Right, so let me just take a minute more, and you simplify over here, and you get back the result. We can do some pretty difficult integrals, such as this one over here from Ruby, and we can do this one from our own test suite quite nicely. The documentation is looking really nice with Itai's hard work, and we should have a new ref page for integrate in version 12. And my last point for just a minute is going to be that we went from high level to college, and from college we want to go to high school, and we now have a new interactive calculus course. I did 50 videos over the last 6 months in this very Wolfram building, and thanks to work by the training group, we now have a complete interactive calculus course with quizzes and whatever you like. It's available to everyone free of charge. You're welcome to try it out, recommend to other people, but that's a big leap for us. So finally, where are we headed in future? Well, we want to go into linear algebra and talk about a course for linear algebra. We finished solving one book. We want to do more, and we have a workshop this afternoon which will discuss that in more detail. But basically my point is that calculus and algebra are in very good shape. We've got plenty of stuff in version 12. We'll have much more coming up later on for pre-calculus, college calculus, algebra, advanced, etc. We're going to keep going, so thank you very much.